shortly. Okay, so welcome everyone to the first online symposium on decision-making under deep uncertainty, also known as DMDU in health. I'm very excited to have this event with you just the week after the in-person DMDU annual meeting, which I missed, but I feel like you will hear from some people that were there, and I hope that you get some of the DMDU content online instead of going to the meeting. So before we start, I just wanted to make sure you know that this is the first online symposium hosted by the DMDU in Health Special Interest Group. The special interest group is affiliated with the Society for Decision Making Under Deep Uncertainty, and I'm the membership chair of that society, and I'm also the chair of this special interest group. So I'm very excited to see this event happening and kind of expanding the pool of people that hear about DMDU applications. Just so you know, we meet every quarter to share work that addresses deep uncertainty in health policy decisions. There's a QR code that you can scan to register to join our group. And yeah, very happy to bring this group together. So just a few housekeeping rules. You should mute your microphone unless you're a speaker. You're very welcome to turn on your camera. You can use the Q&A function or preferably the chat for general comments and questions. Each session will have a dedicated question and answer time covering multiple presentations, so that will be very clear in just a minute. And this symposium is being recorded and will be shared with registered participants. So we structured this symposium in 4 parts. There will be a first talk that will cover some foundations of the decision-making in the deep uncertainty field, and Robert Lempert will lead that session. Then after that, we will all go to the second one, which will cover parametric and structural uncertainty. And that will include presentations from myself, Mirre Scholte at Radboud University, Trikalinos and Shaun from Brown, and Sinead Morris. Then we'll have a little bit of a break. This will be a long symposium, about 3 hours. And then after that, we will dive into addressing inequity in health outcomes with 2 presentations from Tatara at Aragón and Laura at Tradeoffs. But DMDU is really just not about modeling. It's not only about figuring out the best decision. It's also about making sure that those choices are made. And so we'll have a small session on leadership processes in institutions. I'm very glad to welcome Crystal Watson from Johns Hopkins to talk about her work on that, and also Tomás Aragón, who is the California DPH, Department of Public Health Director. Okay, so with that, I am very honored to introduce our first speaker. Robert Lempert is a principal physical scientist at RAND Corporation, and he really has been at the forefront of developing these new approaches for decision-making under deep uncertainty and applying them over, I think, the last 2 decades, but it might be a little bit more. So its work influenced policymaking across multiple domains, including climate change, I think most famously. So yeah, Rob, you can get started.
Great, thank you, Pedro. Let me get my slides up for sharing. Let's see, share, and great. So hopefully, let me get, great, good. So hopefully everybody can see my slides. Okay. Great, okay. Good. So welcome, everybody. Real pleasure to be here with you today. So I'm going to just give a brief overview of DMDU to kind of frame some of the discussions to come. So
maybe you want to swap the displays.
Excuse me?
Swap the displays because we see the wrong screen. We see the one that.
Oh, do you? All right. Yeah. Okay.
On the top, yeah, there you go. Top left, you should see a swap displays.
Yeah. All right. Let me just do this. I'm sorry. Just do it this way. Okay. Sharing. Okay. Is this better?
No, we still see the same thing, but I think if you click on the button swaps displays, that is just next to the end show.
There we go. Yeah. Okay, great. Okay. Now you got it. Okay, good. Better. Okay, good. All right. So here's the question that DMDU aims to answer. How ought to scientists, experts, analysts inform decisions, in this case, health policy decisions under conditions of complexity and deep uncertainty? And there's a vast body of evidence that makes that people make, and as individuals and group, their decisions using well-crafted decision aids. Sort of the obvious thing we go to is that such aids could best inform policy by using predictions of the future. That's often true, but in cases where we have deep uncertainty and contested values, prediction-based analysis can cause problems. And I've been thinking of it a lot in terms of this idea of broken conversations, that between scientists and decision makers, where decision makers expect predictions from analysts, even though they may not believe them, which we experts insist provide because we're asked, and it's what we often like to do. And then the conversation between scientists and experts in the public, scientists, experts often may feign more certainty than they possess because the public rarely listens to doubtful experts. So, what do we do? So fortunately, there's a better way than this prediction-based analysis, which is what DMDU is about. So I'm going to try to tell you that story. So it's not like we have, don't have ideas about what we ought to do about this. There's Francis Bacon writing many centuries ago, says if we begin with certainties, we shall end with doubts. But if we begin with the doubts and are patient in them, we shall end in certainties. A little bit more recently and pithily, Dwight Howard famously says, plans are useless, but planning is everything. More recently, the sciences of complex systems tell us that there's a big difference between complicated systems on the right of this Cynefin framework, which may be difficult to understand, but are subject to reductionist style analysis, where we pull apart understanding the individual pieces, and then we can assemble the understanding of the pieces easily into an understanding of a whole. To complex systems where there's all sorts of feedbacks across components of the systems, across scales, which makes these systems possible to understand, but often very difficult to predict. And importantly here, require different management strategies than complicated systems. So how do we reflect this wisdom when we do quantitative decision and risk analysis? Another concept here is the idea of decision support, which is the science of providing information into decision processes. And one thing you see in the science of decision support is that it often focuses as much on processes as it does on the particular information products. And so here's one decision process. This one comes out of the national security environment, but it's useful because it was developed actually for fighter pilots. So it's a framework that really highlights fusion, uncertainty, and fast decision-making, even faster than many public health decisions. And basically it has 4 components: orient, decide, act, and observe, which gives you ODA. And decision theory, decision tools can focus on essentially 2 big pieces of this, which is one of the reasons this framework is nice, is there's down below is the choice. How do we select among the best options for the menus of those available? But in addition, this idea of framing. How do we define the problem in a way that opens up into thoughtful consideration? And decision support can really usefully contribute to both of those, even though a lot of times we just immediately go to choice as opposed to framing. And so how can decision support best support these 2 tasks? Okay, So what's DMDU about? Traditional policy and risk analysis, which is commonly widely used in many fields, including on health, really takes the form of this, what we call predict then act. So, and it's called that because we begin with consensus understanding of future decisions. All the parties to the decision, are convinced that this is the way to proceed. Sometimes this is often you see this as like a point forecast, but properly a consensus understanding the future would be an enumeration of potential future states of the world and joint probability distribution. So that is a single best estimate distribution. Once we have that consensus understanding, we can take our decision options, some sort of utility function, rank the options from best to worst, and then we may do a little bit of sensitivity analysis. And this is often a really powerful work. Predictions are the foundation of the scientific method. They demonstrate mastery. And it gives you, a definitive answer from the analysis. This is the right decision. However, predict then act can break down under these conditions of complexity and uncertainty. So instead of the crystal ball, you get tunnel vision. And a little bit more precisely, uncertainties are often underestimated because everybody realizes that if you admit how big they are, then you can't say what the best plan is. The analysis falls apart. Problem framing can be skewed towards the demands of prediction. So in other words, we focus on the parts of the problem that we can predict better, and ignore them where we actually don't understand, we find it harder to predict, but which nonetheless may be at least as important as the parts we can predict. And this putting a lot of energy into trying to always be reducing our uncertainty and make better predictions can distract the attention from using what we know to craft solutions that do well across a range. So, and to give you a definition, deep uncertainty occurs when the parties to a decision do not know or do not agree on the likelihood of alternative futures or how actions relate to consequences. So in short, that, predict and act breaks down. So what do we do instead? Under conditions of deep uncertainty, it's often best to begin the analysis from the end. So instead of starting with a consensus understanding of the future, we begin with goals and plans. What are we trying to do? What's our current best understanding of how we might get there, or options for how to get there? Then we use our analytics to answer a different sort of question. In particular, under what sorts of futures, what assumptions about the future best distinguish futures where our plans are consistent with our goals from those futures where our plans are going to go awry. They're not going to meet their goals. And once we understand, or if we've got plan A or B, what are the futures where A is clearly better than B, B is clearly better than A, and where we can't, the futures where we can't tell. Once we have that sort of information, use it to build new or more revised plans that are more robust, which do better across a wider range of futures, make the range of futures where the plan is consistent with goals much larger, and the range of futures where the plan is inconsistent with goals much smaller. There's a whole variety of ways to that, which fall under this category of decision-making under deep uncertainty, and I refer you to this book, which came out a couple of years ago, which gives a pretty good understanding of the field. And this DMDU supports the iterative framing and reframing process that's often very useful for these contested complex problems, which fall under, we often see in health, which fall under this category of wicked problems, where we can't predict the future and people disagree on values. Okay, so just to give you a brief summary, DMDU includes two important pieces. One is the analytics, which focuses on multi-objective. We're trying to achieve multiple objectives, not say just health outcomes, but health outcomes, economic outcomes, kids in school, et cetera. multi-scenario. We're looking across multiple scenarios, and we use our models as exploratory tools, not as predictive tools. So the models explore the relation between assumptions to mapping of assumptions to consequences without making a statement that any particular set of assumptions are correct. DMDU also an important stakeholder engagement process, which is appropriate for these wicked problems where people disagree on values, disagree on the future. So just in brief, not prediction, plan over multiple futures. And really, we're managing uncertainty by identifying robust plans whose choice is insensitive to what we don't know. So I'm going to give you a very quick tour of these two pieces, the analytics and the situation and the stakeholder engagement. I'm going to show you some analyses, not to give you any deep understanding of the content of the analysis, but just give you a sense of what they're going to do. So analytically, when values are contested, there is no optimal strategy, only better or worse ones. And one captures that with what are called these Pareto frontiers, multi-objective Pareto frontiers. And so a simple example is a problem where we have health outcomes, which go from good to bad. There may be economic costs, from good to bad. Ideally, we like to be in the more living corner, have grade on both, but we aren't wise enough, or the world doesn't allow us to get all the way there. And there is the little red dots are the range of feasible solutions. So we could be really good on health outcomes, bad on the economy. We could be bad on health outcomes, relatively good on the economy, or somewhere in between. And there's also a whole bunch of other solutions which are clearly worse. And so while the analysis can't tell us the red dots we want, it can tell us we very much want to be one of the red dots as opposed to any of the other possible things we could do. Okay, and there's a variety of ways to calculate these red dots. Just to give you a quick example, and this is work that Pedro did, this is looking at how various US states might come out of COVID, having initially put on very severe non-pharmaceutical interventions. And again, not to go into any of the details of this, but we model policies not as a specific do this or that, but in a control theory formalism where we say we monitor something and then we might take these responses. In the sort of baseline scenario, there are a whole variety of we looked at a whole variety of strategies, and the ones along that gray line labeled A, B, C, D are the best. And they, so again, the analysis can't tell you where to be on that line, but it can tell you your options, and it can tell you what the bad solutions are, and the ones that you shouldn't do. What we do is we find here, we says that a whole class of strategies that use constant thresholds are dominated by strategies which are a little bit more time or varying. And in fact, this is what many decision makers in many states eventually ended up doing. We can also then do this exploratory modeling idea and look over a wide range of scenarios. And this shows looking at over a whole wide range of scenarios that, again, you get the same answer, that these particular types of strategies dominated and other types of strategies always dominate, even over a wide range. So this is the sort of answer and an example of what you mean by robust. Let me give you a quick then tour of this idea of stakeholder engagement. DMDU employs a process called deliberation with analysis, which basically involves parties to a decision coming together, defining their initial objectives, options, uncertainties they worry about, other parameters. That guidance who create visualizations, other products, give that back to the deliberating parties, who may then change their objectives, options, and parameters, and you go in this iterative cycle. And this facilitates co-production of the information projects, enhances their legitimacy, salience, and relevance to the decision maker. Let me give you, from another domain, sort of a large-scale example of this. This is work that some of my RAND colleagues did about a decade ago for the Louisiana State Master Plan for Sustainable Coast. Just in brief, after Hurricane Katrina, Louisiana had a lot of try to reduce flood risk, reduce land loss, and deal with a whole variety of other objectives. Like you could enumerate them as about 6 key objectives, but there were lots of different options that the various stakeholders put in. River diversions, marsh creations, other restorations, structural risk reduction, and non-structural risk reduction. And despite the fact the state had, many billions of dollars, once you added up all these projects people suggested, you had, it would cost way more than that. So people needed to deliberate, needed to talk to each other about what the best plan would be. But you very much needed analytics and models because the performance of all these projects are really strongly linked. If I build a levee in front of my parish, and if a hurricane comes from a particular direction, the waves may bounce off my levee and flood you, and vice versa. So we really need to work together in how we put together all these different projects. So that's what we did. Took them through this process of deliberation with analysis, kept producing risk maps, these multi-objective trade-off curves, a large group of people working with a large group of organizations, eventually agreed on a plan that passed the legislature unanimously, which is a pretty good outcome. And it was also a quite dramatically different plan than before. So this is an example of inserting decision tools of DMDU decision tools into these contested stakeholder processes. So just to conclude, embracing deep uncertainty may sound scary, but it in fact can help empower decision makers. It can help them identify low regrets, adaptive, diverse solutions, which are robust, helps them place confidence in their plans, not predictions, and can help repair these conversations among scientists, decision makers, and the public. So I know there was a quick overview, but hope that helped give it at least an initial introduction to some of those concepts. So thank you.
Thank you, Rob. It was really good. I'm really happy to have your introduction to this series of talks that now we'll dive into some applications in health and other kind of health issues. So let me share this screen. Okay, so we will have a question and answer session after this group of talks that kind of are more related to modeling. And I think if you have questions for Rob, you can also write them on the chat and he can address that as well.
Yeah, happy to answer questions in the chat.
Yeah. Okay, so I will dive into my presentation. So I will talk about demonstrating robustness in health policy choices and a few applications that kind of put those principles that Rob introduced in practice. So I will cover 3 papers that are kind of related to 2 questions. So the first question is when and how to screen for colorectal cancer. And within that set of questions, I have 2 papers. One is stress testing the United States colorectal cancer screening guidelines. And the second one, looking at the characteristics of a cost-effective blood test for colorectal cancer screening. Collaborators in this work include, I think, prominently Karen Bruder at the Fred Hutch, but also the whole Sinead colorectal cancer group. And this work is NCI funded. And also a separate set of stream of work is looking at the value of environmental sampling surveillance for pandemic response. So here, kind of different kind of problem, more of a population level infectious disease problem. And here collaborators are Henry Reelis and others at RAND. It is also a RAND and NIH funded project. Okay, so starting from colorectal cancer. So there are a few crucial questions in colorectal cancer prevention that are kind of relevant to these papers and are relevant today. So colorectal cancer screening is recommended to everyone in the United States from 45 to 75 years old. You can do FIT every year, the stool test, or you can do colonoscopy every 10 years. But about 1/3 of the screening eligible population is not up to date with screening. And there are a few other complications there because now we also have guidelines that are at odds. So we have the American College of Physicians guideline for colorectal cancer screening, and United States Preventative Services Task Force guidelines. There are also others, and the way that they diverge is the age to start screening. So the new USPSTF guidelines recommend starting screening at age 45. ACP kept the recommendation of starting screening at age 50. So there's some disagreement there. There are also new things. Now we have blood tests that can detect cancer, and these tests aren't available. So a crucial question will be, should guidelines endorse these tests? Should payers cover them? And should people generally use them? And CMS already has a position on that one. So starting with the guidelines issue. So the key question that we address in that paper is, are USPSTF and ACP guidelines efficient when you consider a wider range of assumptions that are more challenging that we have assumed before? So what if colonoscopy sensitivity is lower than assumed? What if the natural history uncertainty now is considered in a more thorough and rigorous way? And what if we make different assumptions about adenoma onset? This is a slightly long paper, so I'll just cut to the chase and show you results. And if you're interested, you will be able to see this paper very soon in the literature, I hope. So what we find is in this paper is when we look at a wider range of assumptions. So now we are looking at two model specifications, varying assumptions about when adenomas start. And we also consider uncertainty via a Bayesian estimation approach. And we also look at 4 plausible colonoscopy sensitivity scenarios. What we find is that the uncertainty bounds of effectiveness is wide. So in this graph, you have colonoscopy per 1,000 people and life years gained. So you want to save as many life years as possible using a small number of colonoscopies. And what you find across these two model specifications that make fundamentally different assumptions, that this strategy that starts screening later is always dominated. So yes, the uncertainty bounds are wide, but no, the ACP guideline is not at the efficient frontier. But one of the things that can be not clear when you look at this is that whether or not this strategy is efficient in every single of those parameter points, right? It can be dominated in expectation, but maybe there is some parameter set, some assumption about how this disease works where this strategy actually works, is in the frontier. Well, we look at that and the answer remained no. So that result holds for every single parameter set that we looked at. And the way that I visualize this is using this little plot where you have colonoscopy sensitivity, different assumptions here. Each of these kind of facets is a strategy in that assumption. And so, and the efficiency status here, the color represents efficient. ED stands for extended dominator, just dominated by a combination of strategies, and D is dominator, meaning it's more expensive or uses more colonoscopy, and it gets you fewer life years gain than an alternative strategy. So what we find here is that this strategy here, starting at screening at age 45, ending at age 70 every 10 years, is pretty robust. It's efficient pretty much everywhere, regardless of how what assumption you make about colonoscopy sensitivity. This strategy is the strategy currently recommended by USPSTF, and is efficient or extended dominated or nearly efficient. And it's efficient to the extent that you assume a higher colonoscopy sensitivity, but it can become extended dominated if you have very low sensitivity assumptions. This strategy, on the other hand, is a strategy that is being recommended by the ACP right now. And we find that strategy is either dominated or extended dominated across all these parameter sets. So a key substantive result from this is that we cannot support the ACP guidelines using this model. It's just not consistent with this model. And if you want less intensive screening, then you can either stop at age 70 or test every 15 years. These would be alternatives that would get you less intensive screening, but still be efficient. Okay, so that's that for that paper. Now we're just kind of covering another paper where we looked at blood tests. So there's good news in this field, right? We have now blood tests that are available for colorectal cancer screening. The caveat is that using them every 3 years is not as effective as alternatives, as projected by every model that has been published so far. So the question becomes, what is their role on surface screening? And that is really a DMDU question, if you think about that. So the CISNAC group worked with the American Gastroenterological Association, and the question that they posed was very much a DMDU question, even though they didn't come up with that. They didn't know necessarily the methods. But the question that they asked us was, under what conditions can the blood test be as effective or cost-effective as existing alternatives? If they are not cost-effective right now, can they improve performance? And at which point do they become cost-effective? So there was a panel to review the evidence, and the modeling groups contributed to that panel. So you can look at Lieberman et al. And Clinical Gastroenterology for a description of that work. So the work that I did, and it was a paper involving multiple modeling groups, really aimed to answer this kind of one question. Under what conditions can blood tests match the net monetary benefit of colonoscopy screening? We also did it with other outcomes, but here I will focus on net monetary benefit. So if you think about this question, it's a good question for a DMDU analysis because we don't have necessarily a probability distribution for the performance of these tests. We're talking about tests that will be developed now and they'll be available in the future. So it's a forward-looking question. We just don't have the data, but we still can use the model to investigate what is the region of the parameter space where that test becomes very attractive compared to what we have today. So when we do this analysis, one of the outputs is this map, and what this shows you is the colors represent net monetary benefit. So lighter colors are better, higher net monetary benefit for the blood test. And you have the two key parameters that drove the net monetary benefit in this analysis. We have the blood test cost and the blood test sensitivity to advanced adenomas. And what we can show is that if you do the blood test given a certain frequency, you can get very close to the net monetary benefit of colonoscopy. But to get there, you need much higher blood test sensitivity to advanced adenomas and lower costs to really match that number. And this kind of information is useful for a test developer. I even had a test developer reaching out to talk about this. And they were really interesting because they think it is feasible, it's possible to get at this very high advanced adenoma sensitivity. So that was kind of an interesting outcome of this work. Okay, so this was the second paper that's already available at JNCI. And I think that is kind of one example of the scenario discovery approach. If you're interested, you can look at that paper. So I also want to highlight a third paper where we asked a DMDU question, but we really didn't have to use many DMDU methods. And I wanted to include it here because it's also important to realize when the answer is very clear and clear enough that you don't have to do a lot of the more complicated DMDU analysis. You can just make a strong argument. So let me just walk you through this. So the question that we want to answer here is to quantify the value of environmental sampling surveillance, like wastewater surveillance for pandemic response. So now the United States has expanded the national wastewater surveillance system. Other countries are doing that. And these systems are really good for detecting pathogens because you don't have to test people. You don't have to rely on people's willingness to test. You can just surveil the wastewater and it can respond based on that signal. So what we did is we did a modeling study where public health officials looked at that information to drive their decision-making. And the bottom line result we found is that under base case assumptions, this system could provide about $1,500 of value per person in a new COVID-19-like pandemic. So if COVID-19 happened again, and we had to use this information to make decisions, we could have some meaningful value. And you can see that as you have the NPIs, this is the scenario with NPIs without early warning system. And as you get more early warning, you get less health costs. The NPI costs increase, the non-pharmaceutical intervention costs increase, but the net effect is that you get fewer costs from the pandemic. So you get a positive net monetary benefit. After we did this kind of base case runs, we investigated, okay, how does these value change under a wide set of conditions? So we did a series of one-way sensitivity analysis, and we showed that under most cases, you get positive net monetary benefit. Even for a pandemic that is only half as deadly as COVID-19. There are also other scenarios there, and this paper also employs some uncertainty quantification methods to create these intervals. But the main point is that sometimes there are policy choices that are very robust, and you don't have to have a probability distribution of all your model parameters to make the case for those policies. Okay, so just very briefly, a few reflections. DMDU can seem a little bit overwhelming if you read the papers, and especially if you're not used to kind of seeing that it might be a little bit, intimidating. But you don't get extra points for papers or research that is just difficult to follow. So sometimes if the answer is clear, you can make this a fortiori argument. You can just say that the policy is robust regardless of the future. And sometimes if the answer is nuanced, then sometimes the methods will help, like the scenario discover approach helps you identify conditions under which a decision is robust. So yeah, so I'm happy to take questions later. And now I'm also happy to call Mirre Scholte to present her talk. So I'll stop sharing my screen, which is there.
Yeah, thank you, Pedro. Can you hear me?
Yes, we can. Yeah, so I have a little, just a small introduction. So I'm very happy to have Mirre Scholte from Radboud University give her talk. She's an assistant professor at Radboud University Medical Center, and she'll talk to us about her work on early health technology assessment. So yeah, Mirre, you can take it away.
Thank you. I hope this works. I think it will. Can you see my screen?
Yes. Not in presentation mode, but yes.
Probably now it's in presentation mode, right?
Perfect.
So thank you, Pedro, for this opportunity. And I would like to present our work where we explored the DMDU methods for use in early health technology assessment. And we did this work together with a multidisciplinary team. We had co-authors from the HTA field, so my field, Janneke Grutters and Maruska Rovers, DMDU co-authors Jan Kwakkel and Vincent Marchot, and the clinical team represented by Karin Klein. We published the work last year in Value in Health, so a typical medical journal. So first I want to give you some background of what is health technology assessment and what do we typically do. So health technology assessment assesses the new drugs and technology, typically for reimbursement in the health system. And the central question is whether they provide value for money or not. And we look at the effectiveness in terms of quality of life and life expectancy, and we look at costs. We often use models to predict cost effectiveness, and this is typically done at the point of market access. So if you see here the innovation timeline, which starts with an idea or a problem, and then there is development of the innovation, testing until a large phase 3 clinical trial usually, And then on the point of market access, HTA comes in to assess the new innovation, the drug or the technology. However, if at that point it appears not to be cost effective, a lot of time and resources are wasted. So that is why we look at early HTA to already look from the beginning whether a new technology can become cost effective in the end. And we look at conditions for added value, what are the knowledge gaps we have, and what further research is needed. But we also have some challenges in early HTA because the line from idea to implementation of a new innovation is never a straight line, as you probably all know. There are many different scenarios in which the technology can develop. For example, you can choose different patient populations to target a new technology. Ideally in HTA, we would like to assess all these routes and their uncertainties. However, our methods do lack the ability to test a lot of possibilities at the same time. So how we often deal with this in early HTA is that we make assumptions. And this concerns, for example, the disease, which we select, the patient population, effectiveness, and risks. And as you can see here, these are both choices that you make and also concern uncertainties, like effectiveness or risk. And so how do we go about these uncertainties? If we know a parameter, for example, but it's uncertain, we can use a distribution, and we're quite comfortable doing that in HTA. If one parameter is unknown completely, we can use an assumption and explore that assumption, for example, by taking a minimum and maximum value or multiple values. However, if we have many parameters that are uncertain in the model, then it becomes harder to make sense of the results of the model. And for choices, these are actually made often before modeling. So the disease that we will focus on with the technology, that's often a decision that's not made within the model, but beforehand. So we don't explore these choices at all. And we thought, well, this is alarming and we should do better. And that's why we came up, we searched for the DMDU methods, and we looked if exploratory modeling methods could help us in these circumstances. How we did this is via a study where we compared our traditional early health economic modeling methods versus the DMDU exploratory modeling methods. And we determined whether and how the DMDU methods could enhance the early evaluation of our health technologies. And we did that on a case study using minimally invasive surgery for patients with intracerebral hemorrhage. So that's a subtype of stroke, which is particularly deadly and debilitating. So in HTA, we often use state transition models, which are models that follow patients over time and look at different health states of these patients. And for this particular case study, we used input parameters, and the most uncertain ones are the surgery effectiveness, the costs, and the population, for which we used 3 input populations. Our outcome measures are incremental cost, incremental effect, and the incremental net monetary benefit. For DMDU, we had to add another decision tree to the model to allow for more flexibility in our analysis, as we wanted to explore a lot of scenarios. And we distinguish between uncertainties and policy levers. So now complications was added as an important uncertainty, and we added policy levers, so the population distribution and who receives surgery. So for early HTA, we found that effectiveness of surgery mainly drives its cost effectiveness, as you can see in the two-way sensitivity analysis plot here. So here you see the surgery cost in euros and the effectiveness of surgery. And this line represents the equal net monetary benefit, so where the strategies are equally cost effective. As you can see, at 10,000 euros of surgery costs, the surgery would be effective if it was effective in more than 2% of people, of the patients. So that's a really low threshold. And we conducted scenario analysis that showed that surgery is most cost effective in patients with a poor health state. So patients who are really having a worst type of intracerebral hemorrhage. And for the DMDU results, we generated 1,000 policies and simulated those over 1,000 scenarios. And so the policies reflected the choices that we had in the scenarios, the uncertainties. And we found that surgery effectiveness, the chance of complications, and who received surgery were the most influential parameters. And this was interesting because it contained 2 uncertainties, but also a choice that we could actually influence. And we also looked at what scenarios or choices result in robust strategies. So in this case, robustness was defined as strategies that were cost effective in more than 95% of all simulations. And then we found that the most robust strategies reserved surgery for patients with poor health states. So it was quite similar to the early HTA findings, but in a completely different way. And as this was our first try to use the DMDU approach, we also encountered some hurdles. So the first one is the translation of the results to clinical practice was sometimes quite challenging, as we had to get familiar with these methods, but also the clinicians had to get familiar with those methods. And for example, it's really hard to predict who has a poor health state before the surgery, as that's often known only after a few days once the patient is stable. Second, the approach could not come to its full potential due to the narrow scope of the HTA model. So we barely include choices in our models, and the scope of our model is quite narrow. And ideally, we would include the entire stroke care pathway, for example, in the model, and include multiple choices, among which multiple solutions to the problem. And that's exactly the third thing that we encountered, is that we don't consider multiple solutions to a problem. So in HTA, we always have the solution, the new technology or the new drug, and then we model whether that's cost effective or not. And that really, that hinders to consider multiple solutions. So we should really do better at that point. And last, our DMDU methods are quite complex. So they had a quite high computational burden. So we thought they were not suitable to every HTA problem, maybe. But we were really enthusiastic about the way that DMDU approach this problem, and we think DMDU can really enhance the early HTA. So I think we should really have more of a system or a problem focus instead of an innovation, so a solution focus. We think it might help us if we would focus on robustness first to choose the solution to the problem that is most robust to uncertainty, and then optimize it. While from an HTA perspective, we would immediately try to optimize the solution and consider only one single solution. We thought this distinction between policy levers and uncertainty was really helpful, and that allowed us to have a little bit of grip on the system and also steering the system into desirable outcomes. And as you probably all know, DMDU is a 3-level approach. So we now only looked at exploratory modeling, but we are quite keen to also explore adaptive pathways and joint sense making. And I think if we do all 3 for the same problem, we would actually gain better results than we did now. And that was the paper, and I would really like to thank you for this opportunity. And if you have questions, I'm happy to answer them in the chat or via email or here live. Thank you.
Yeah, thank you for the presentation. So really interesting to see other groups kind of picking up the methods and yeah, exploring them. And I'm very glad to introduce Trikalinos and Shaun at the Center for Evidence Synthesis in Health at Brown University. So if you'd like to start presenting or sharing your slides, you can do that. They will present their work on propagating ambiguity into the decision analysis of test and treat strategies. So yeah, Shaun and Tom, you can take it away.
Yes, thank you, Pedro. Give me one moment to do the Zoom. So all this is Shaun's work, most of it done during his PhD. But Shaun is actually traveling and he's able to join. I saw him. I saw him on the list. So we decided that I would do it just because he's in a noisy environment. So you would have to settle with me and suboptimal exposition, but that's what you get. So this is, I presume you see the correct screen, right?
Yes, we do.
Yeah. Okay. So this is, as I said, joint work with Forbes and Iskandar. Rowan Iskandar is at Medtronic, and we have no conflicts to disclose for this work. And what we shall discuss is essentially a typical HTA. So this was work done for in the context of a real decision-making problem that the CDC faced. The original analysis was more traditional, but we went on to do a different analysis that would be a bit more mindful of deep uncertainties. So in what we will discuss, it helps to think that about uncertainty models in two different as belonging in two different buckets. So you have probability uncertainty models, and this is just a depiction. So maybe I have a quantity and I have probabilities A through E that essentially show densities that describe how likely different values are. And there's also a different uncertainty, a different type of uncertainty model that we can use that may be an uncertainty set. And when we are talking about uncertainty sets, and I tried to line these up and down, instead of characterizing our uncertainty with a probability distribution, we may say that we believe that the quantity that we are trying to describe maybe lives in a set, but I cannot tell you exactly what shape it takes in that set. I don't commit to a specific probability distribution. In fact, if I only tell you that it lives in that set, then you could think about it as I am being compatible with all possible probability distributions that have support over that set. So that's one way of thinking about it. Now, I am going to talk about uncertainty sets in this way, but there are many, many, many ways to describe uncertainty models, and I'm not touching them yet. I'm happy to discuss some of these. So for now, I'm going to use these two extrema, either a probability model or an uncertainty set model. And this is the notion of deep uncertainty in this talk. We are explicating a decision analysis when we are unwilling or unable to describe the uncertainty in some inputs with probability distributions, but we may be willing and able to describe it with uncertainty sets. And this is very much in the spirit of what Pedro said, what Robert said, and all the talks thus far have a flavor of this, right? So, but when we use these types of uncertainty models, it complicates the mathematics and it complicates the choice of quote unquote optimal acts, and that's kind of what we are explicating in this exposition. So this talk is geared maybe for an audience in medical decision making. So I hope it's not pitched too off. Okay, what's the example? So the example is about tuberculosis, and this is a serious disease. And people who have asymptomatic infection, we call it latent tuberculosis infection. They don't exhibit symptoms and they cannot spread the disease. But if they are not treated, the disease can flare up. And if it becomes active tuberculosis, it may spread to others. The idea is that risk of latent tuberculosis infection varies by country, and therefore a policy problem appears. And that policy problem, if you boil it down to its basics, is the following. If in the US, we should screen immigrants from high-risk countries for a latent TB infection or not? So that's the policy question. And there are many trade-offs, and there are many things that are going in one or the other direction, but, you know, just for nailing down ideas and moving forward, I will describe only the obvious trade-off, which is you can treat the identified cases, and if you treat them, it greatly reduces the risk of an outbreak. It also improves their own health and so on. But the tests that you could use to do this screening have a performance that is not well understood. And also we have limited resources. So we have this trade-off that we are facing. The tests are several, but you can boil them into two categories. So one is the Mantoux test, which is essentially a skin reaction. So you give an inoculation with some diluted mycobacterium, and after 3 days you have a so-called delayed hypersensitivity reaction. And then you can go on and measure how big this reaction is, and you measure it with either calipers or a scale, and you're not supposed to measure the redness, you're supposed to measure the induration, how big, you know, the firm tissue is. This test is difficult and subjective to do. So I've done it. I am a clinician by training. I don't practice anymore, but when I was in clinic, I have many times measured these types of tests, and very often I was disagreeing with my attendants and so on. And you know, it's also difficult because you have to come back after 2 to 3 days and maybe repeat it. Sometimes it becomes false positive because it cross-reacts to mycobacteria that do not cause TB in humans. So it's not as specific as this other test, which is the interferon gamma release assay, the IGRA. This is a blood test. You just take it within 24 hours, you have results, and it may be more specific. So that's the setup. Let's move on now and think the analysis of this policy problem. I told you already I have a decision maker. I told you what the beneficiary of that decision would be. And how do we think about this? We're saying, okay, we first define the available acts. Then we have to describe our uncertainty about the state of the world. And then we would need a way to kind of like say, what does this uncertainty implies about the certainty or uncertainty that we have about the outcomes that interest us. And after we do all this, what does this mean about which action is best, and best in what notion? So I'll walk through these things as I go through. So what are the available acts? I have 2 screening tests, and when I have 2 screening tests, I can induce approximately a dozen different screening policies. But here, the practically implementable policies are the ones that I show here. So there's 5 practically implementable policies. One is that you do nothing, and I will be calling that no screening. But also I test no one and I treat no one. Another one may be to apply one or the other test. And then the other is to cascade the tests. So I give first the one test, and if someone is positive, I will give the second test. So these are 5 strategies that are going to be considered. And T1 is going to be the skin test, and T2 is going to be the interferon gamma release assay, and pretty much that's my policy space. Okay, so how do I think about my uncertainty about the state of the world? And In this case, I have many uncertainties, but for the sake of discussion, I will focus on some, just to make things a bit more concrete. So I have uncertainties about the prevalence of the latent infection in various immigrant populations, may be stratified by disease or not. I'm not going to get into a lot of details, but I have uncertainty about prevalence, about the screening performance of the tests. I also have uncertainty about how people will adhere to testing and treatment plans, how effective the treatment is, and what is the likelihood and size of a TB outbreak. But I will actually say, for the sake of exposition, and just to keep us going, I will focus only on the uncertainties that have to do with testing. And all the other uncertainties, I am willing to consider them either as describable with a probability distribution or fixed to some particular values. This does not induce great loss of generality in what I will describe here. And also, you could do the same things that we will describe here for the uncertainties that is not the focus here. So what do I mean about uncertainties and how to describe them? These two tests that we have are imperfect. There are fallible tests. And we are trying to understand where these inputs that have to do with test performance live. And what we have as data is cross-classification of the test results. So we have studies, we have 41 studies in this analysis, but I will just focus on one that cross-classify, they give the two tests in immigrant populations, and then they can describe the probability that these tests agree jointly, saying that they agree that the result is positive or the result is negative, or they disagree in different ways. But these are cross-classifications between two imperfect tests, and I don't have data about the results of the tests and an infallible gold standard. This means that if I'm delving a bit deep into this problem, the probabilities that I have in these 4 cells correspond to 7 parameters. The prevalence of the disease in the population where the study was done, the sensitivities of the two tests, the specificities of the two tests, and the covariances in the sensitivities and specificities. These covariances are the extent to which the two tests agree beyond what they should agree by chance, either in one or the other direction. And that means that I have more unknowns than data. I have 4 cells, but they are linearly constrained. So I have 3 degrees of freedom, and I have 7 parameters. And when I have more unknowns than data, I cannot point identify identify the vector of the parameters that I'm dealing with. And although, remember, we are focusing only on these diagnostic parameters, you could have similar discussions about the other parameters that I'm willing to say now, put distributions on them. So I cannot point identify them. Now, in the typical Bayesian analysis, or in a typical latent class analysis, you put distributions on this vector of parameters, and therefore identify them through the prior distributions. But I don't want to assume a prior probability distribution for this Z. Instead, I want to make minimal assumptions to the extent that I can. So we will make assumptions that are of this sort, that say the tests are non-adversarial. What does this mean? It means that their ROC curves are going to be either on the diagonal or above the diagonal. So when they call the disease, they're more likely to call the disease rather than non-disease. And that's a pretty innocuous assumption by construction of these tests. And maybe we are willing to make this second assumption or not. I'm going to show you results that do this, that IGRA is more specific than TST. So meaning, and there's a very good biological rationale why to do this, but you could relax that assumption as well. So if IGRA is more specific than TST, then the specificity of that would be higher than that of TST. So what does it mean? It means that if I have a study, and if I take a realization of a study, and now I showed you a table with probabilities, now I'll show you a table with counts. I have some counts in here, and these counts essentially constrain where on this 7-dimensional space these parameters live. Now, this is a finite sample, right? So I have uncertainty around those counts that is sampling uncertainty. But just to not complicate the discussion, I would invite you to imagine that you have an infinitely large study with the same relative proportions. Even with infinite data, you cannot point to identify the 7 parameters. You would still have these parameters living in a subsection of the 7-dimensional space. And this discussion going forward will assume that I don't care for sampling uncertainty here, but in Shaun's analysis, we actually incorporate sampling uncertainty on top of this on non-identification region. So the uncertainty set that we use is not a probability distribution on this, but it is saying that these vectors for these parameters, they live in a subspace, or not subspace, in a subpart, in a subregion of the 7-dimensional space that we will call U. And that U is all the values that are feasible based on the observed data. So this means that you can imagine that if I take a plane for the sensitivities of the 2 tests, and that plane slices through the 7-dimensional space, maybe the parameter values that are compatible with these data live in these blue regions. Okay, so this is kind of like the slice of this plane through that space, and this image is real, but it's from a different set of assumptions. I couldn't very easily get one from Shaun's thesis. So the thing now is, okay, I described this uncertainty set, and what does this imply about the things that I care about? So how does this uncertainty in test performance propagate to uncertainties in outcomes? And what we do in these cases is that we say, that's the put-put framework. So there's a set of inputs that are consumed by the model, and then you get the output that you are trying to see in the future, and you are trying to do this for the policy space that you're facing. So usually we write it like this, and like this is a map. The model is a map from a realization of the inputs to the realization of the outputs. And here we would have a model. My inputs are going to be the test performance parameters, my other inputs, and my policy. And I put the other inputs in a gray just to say they are there, but I'm kind of like putting a probability uncertainty model on them for now. And I am going to put an uncertainty model that is an uncertainty region, an uncertainty set on the test performance parameters. And then I get back a vector of outcomes, and I'm going to simplify this and say, let's say that I'm interested in net health benefit that collapses everything in health units. So it takes the monies and a willingness to pay and makes it qualis, it makes it health. So the net health benefit would say bigger is better. So in the typical case, as I said, we would propagate the uncertainty in the inputs to an uncertainty in the outputs. And if the inputs have a probability uncertainty model, then the outputs would have a probability uncertainty model. So, if this encompasses deterministic models in the sense that the deterministic models that have fixed parameters, you can see them as point masses, distributions that are point masses. So probability inputs, probability outputs. Right? And here what we are saying is that, well, if the inputs are described as uncertainty sets, then if you work through the mathematics of that model, you can show that the outputs are going to be described as uncertainty sets. And in our case, they're going to be described as these intervals. They're open intervals, and they're compact. In order to describe them, you just need to know it's their minimum and maximum value. So let me, the propagation of uncertainty that happens is that I have this model now. There's an economic model that we have developed, and we now shift its analysis and put some inputs as uncertainty sets, and we get as outputs some uncertainty sets. So as I said, you can show that the only thing you need to describe these uncertainty sets is to find the minimum and maximum possible values that the net health benefit gets with each one of the strategies. And to do that, you can essentially specify and solve a mathematical program. And what you're doing is that the blue part shows the upper bound, the red part shows the lower bound. And what you're saying is, what I'm doing is like, I'm going to find I'm going to take all the probability distributions or fixed values out by an expectation, and I'm going to find what is the maximum net health benefit that I can attain over the whole region that Z can take, subject to some constraints. So the description of the model, I'm not going to go through it, but I showed you these things in the table. When I showed you the partial identification case, the yellow part always holds. These are the so-called Hefting-Frechet bounds that always hold. So this is not an assumption. It's like just mathematical truth. The salmon part says these are probabilities. They live between 0 and 1. And then the only assumptions that we are making is the things in the green part, that here I have a specification of the problem where Shaun assumed 0 covariances and non-adversarial tests, although the results that I'm showing you are assuming that IGRA is more specific than TST. Again, it's like what I could screen capture relatively easily. Okay, so I have this situation now. I have projected my outcomes into ranges, but now it's difficult to say which act is best, because you can always order single numbers, and the technical term for that is that you can assess a weak order over single numbers, meaning if you give me single numbers, I can tell which is bigger, which is smaller, or when there's a tie. But if you give me intervals and say, tell me what is best, I cannot always order those intervals, those sets, in a simple way. And that's kind of like this discussion that follows. So I already said that if I have uncertainty, that is probability models, the output is a probability model. So I can always assess a weak order. I can always say what is best, and therefore I can always choose by max expectation. I can always choose the thing that maximizes the expected net health benefit. So if my outputs are point masses, this is trivial. If my outputs are distributions, then some statistic of the distribution, in the usual case, the mean, is orderable, assesses that weak order. But if I have sets, then what I know is somewhere in there is the expected net health benefit, but I don't know exactly where it is. And these are therefore situations where I assess a partial order, meaning sometimes I can say which net health benefit case is better than another, but sometimes I cannot. So here's my situation. One way to think about it is, and I'm going to run through some choice functions, and I understand I need to speed up. I'm running through some choice functions, and one idea is like, can I say what is best based on non-overlapping intervals? That's not exactly correct, but it's kind of getting the point across. So here, take a look at no screening. You can immediately see that the best case with non-screening is worse than the worst case with T1 and then T2 and then T1, T2 and T1. So I can write it in this way. So I'm building what is known as a Hasse diagram for partially ordered sets. But if you take a look at no screening and T1, then T2, you see that they overlap even a bit. But if they overlap even a bit, I cannot tell which is best. So I am going to put that as not really able to compare with no screening. And in my optimal sets, I have these strategies that are not clearly, let's say, excluded. In this case, I can do something better. because I can show that in some scenarios, some assumptions, I can mathematically show that there is a pointwise alignment in some strategies. So this means that even if, let's focus on let's say T1, T2, and then T2, T1. Even if these two overlap, if you take any realization of the world, it's always going to be better with the purple strategy. This means, therefore, that I can assess a different order, and my optimal sets become T2, T1, and then T2. And that's the idea of using maximality as a choice function. If I am a pessimist, maybe I want to focus on the worst case and say, I will consider the worst possible outcomes. In such a case, if you take a look at the worst possible outcomes, T2, T1 is best. And if I am an optimist, I am going to take a look at the right-hand side of the intervals, and I assess the best possible outcome. And people have seen that before. There's a notion in which case a way that I can create a hybrid objective and mix the best and worst outcome and kind of like have a tunable degree on decision makers' optimism or pessimism. And if I do that, then I mix the best and worst cases. And if my tuning is favoring if my tuning parameter is this 0.5, then if it's less than 0.5, I would favor one thing or the other. So if I take a look at this whole situation, then I have looked into this non-identifiable case with different choice functions, and interval dominance usually gets you the biggest set. It cannot exclude a lot. Maximality usually reduces this set a bit more. But both maximality and interval dominance have the property that if I narrow my uncertainty set, the optimum set becomes smaller. Pessimism and optimism and Hurwitz return a single policy. And if I contrast that with, and if I see what the distribution-based analysis did, it said that the optimal acts were T2 were acts that include IGRA as a testing policy, and different acts were better in different scenarios, but it kind of aligns. So I'm kind of feeling a bit better about my Bayesian assumptions that were really humongous in that Bayesian analysis, because it aligns with this minimal set of assumptions that I do above. So, I mean, someone can ask, what is the correct choice function? And that's a deeper discussion. There's no correct choice function. They capture different attitudes to ambiguity. And there are some implication relationships between these functions, but I'm not going to get into this. And some parting comments is that there's different models of uncertainty trade-off assumptions for reach. So if I make more assumptions, I have further reach with my Bayesian analysis, but I also have reach in the wrong direction as well. I may be confidently wrong and spectacularly wrong more often. And it's straightforward to use both probability and uncertainty set models in the same analysis. And then there's a whole set of a whole way of discussing these types of analysis and reaching conclusions and feeding back to the decision making persons. So I did kind of like do that as a polar set of opposites, like probability distributions versus uncertainty sets. There's a lot in between, but it kind of is describing like the two extremes, at least as we were thinking about them. So thank you, and sorry if I went a bit off.
That was great. Thank you, Tom, for the presentation. So really nice to see some kind of more analytical work in this area as well, I guess. Yeah. So now we will go to our next speaker and final speaker before our break. We might have a little bit of time for discussion, but I'm not sure we have much time. So yeah. So Sinead, Morris, if you're there and can join us. Yeah. So I'm very happy to introduce Sinead Morris. She's a consultant for the Centers for Disease Control and Prevention at Gold Belt Professional Services. and she'll present her work on the detection of novel influenza viruses and its implications for surveillance efforts in the United States. So yeah, Sinead, you can take it away.
Great, thank you. And can I just double check that you can see the slides okay?
Yes, I can.
Great, thank you. Okay, so I'll just jump straight in. So today I'm going to focus on some work we've been doing around novel influenza viruses and surveillance for those viruses in the US. And as many of you are probably aware, these are influenza viruses that are different from the seasonal influenza viruses that circulate in humans from year to year. Instead, they usually circulate among animals, but occasionally spill over to humans where they can cause serious morbidity and mortality. They also have the potential to cause widespread pandemics if they gain the ability to spread from human to human. And because of this, it's really important that any novel case of influenza virus infection is rapidly detected so that public health agencies can figure out what kind of virus they're dealing with and can start to implement any necessary public health measures. And so avian influenza virus, or H5N1, is one such novel virus. Since 2022, there have been widespread outbreaks among wild and commercial birds and other mammal populations around the world. And in the US this year, we've also seen outbreaks among dairy cattle. And so in this year in the US, there have been 55 reported spillover infections in humans, mainly in workers who've been exposed to infected cows or infected poultry. But at the moment, there's no evidence that the virus can transmit between humans, and so the risk to the general public is thought to be low. However, if the virus were to gain the ability to transmit between humans, and we started seeing cases occurring in the wider community among people with no history of exposure to infected animals, then we wanted to try and understand if those cases could be detected by existing surveillance systems that we have in the US, so that public health action could be taken as fast as possible. And so the US actually has robust surveillance systems in place for seasonal influenza, but primarily through testing that's conducted in various healthcare settings like outpatient clinics and hospitals. And so in 2023, when we started this work, we wanted to look at how those systems might be able to detect cases of novel H5N1 and where additional resources might be most efficiently allocated if needed. And so our main aims really were to estimate the likelihood that cases of novel H5N1 would be detected through existing testing surveillance in different healthcare settings. And this was assuming that cases are occurring at low levels in the community, so very early on in an outbreak, and would have no known recent exposure to H5. So there'd be no obvious risk factors that would increase their chances of being tested compared to someone else presenting with general flu-like symptoms. We also wanted to know, which healthcare settings might be more likely to pick up cases. So are there places where future testing efforts could be targeted? Also, how many tests might be needed as part of those efforts? And then how might future unknowns like disease severity and changing testing practices impact things? So the framework was actually adapted from previous work developed by colleagues at CDC. It's pretty simple, but it has the advantage that it leverages a lot of existing data that we already had and was something that we could stand up relatively quickly. And so the general idea is that we assume that there are a certain number of H5 cases in the population. Depending on their symptoms and their care-seeking behavior, they may present to a particular healthcare setting, such as an emergency department or a hospital. And then depending on the testing practices in that setting, they either will or they won't be tested for flu and potentially identified as the case. But then at the same time, there's also background circulation of other respiratory infections in the population that can cause people to present to care with symptoms very similar to influenza. So all of these healthcare settings will also be testing people who aren't infected with H5N1, but have something else like seasonal flu or COVID or RSV. And so this framework not only takes into account the testing that will take place among people with H5N1, but also the tests that are needed to rule out H5N1 among people presenting with other infections. And so the most important part of the framework is how we calculate the probability that a given case of H5N1 will be detected in a particular setting. And that involves accounting for all the steps that must happen in order for that person infected in the community to end up being detected by testing surveillance. So the first thing is they have to develop symptoms. They then have to seek care for those symptoms in a particular healthcare setting. They also have to be tested in that setting, and testing has to take place while they're still shedding detectable virus. The test also has to correctly pick up a positive result, and then any positive test has to be forwarded to a public health lab to confirm infection with H5N1, because seasonal flu infections would also show up as positive on the standard tests that are used in clinical settings in the US. And then by quantifying how likely each of these steps is to occur, we can then estimate the overall probability that this case will make it through all of those steps and be detected. So I don't have time to go into the parameterization of each step, but for the majority of them, we define prior distributions that are informed by data from existing influenza surveillance platforms that are in place across the US. And then when we simulate the model, we draw from those distributions in order to capture underlying uncertainty in each of these parameters. There are also 3 different healthcare settings that we considered here. So we had urgent care and emergency departments to represent milder infections that would require people to report to outpatient clinics. We also had hospital settings to represent more severe infections, and then intensive care unit or ICU settings to represent those most severe infections. And then we also compared healthcare testing to a hypothetical strategy that would actively test people in the community regardless of their symptoms. So some important points to note are that the probability an individual is tested will vary depending on the healthcare setting. And the one parameter that we didn't have a great handle on is that last parameter for the probability that a positive test is forwarded for confirmatory testing. And so in the main analysis, we assumed that it was 50%. That was following a study that was done in hospitals prior to the COVID pandemic. But then we also considered a range of values in sensitivity analyses. And then the last thing that I want to highlight is that these parameters for developing symptoms and seeking care will likely vary depending on the severity of the disease. So for example, with seasonal flu, many people experience no symptoms or mild symptoms that can be treated in an outpatient setting. But for more severe flu viruses, for example, those that have been seen in previous pandemics, then we might expect more people to have severe infections that require hospitalization. And so to account for this uncertainty, we defined 5 different possible scenarios for disease severity. And then for each scenario, we varied how likely people were to develop symptoms, and then how likely they were to seek care in each of the 3 healthcare settings. So the top row here, this is just showing our parameters for the baseline scenario, which were based on seasonal influenza. And then going down the rows, we have scenarios for increasing severity. So the second scenario here is loosely based on COVID-19. So here we assume the same chance of developing symptoms and presenting to outpatient clinics, but a greater chance of being admitted to hospital or the ICU. And then in the third and fourth scenarios, these were chosen to represent intermediate levels of severity. So here we assume a greater chance of developing symptoms and also presenting to each of the healthcare settings. And just as an example, so the chance of being admitted to hospital in that first intermediate scenario, that was chosen to represent something similar to the 1918 flu pandemic. And then the final scenario here is something closer to the severity that's been reported for previous H5N1 infections in humans prior to the spillover events that we've been seeing this year. And we use this as our most extreme scenario to make sure that we were exploring the a full range of possibilities. And then when we run the model, we simulate each severity scenario and each healthcare setting separately, and we sample parameter values from each of the ranges that are shown here. So this is just walking you through some of our key findings from this analysis. So here the x-axis is the severity scenario, and the colors are the different settings. So green is the community setting, orange is urgent care emergency departments, then we have the hospitals in purple and ICUs in pink. The points here are the median values from 1,000 simulations. The inner shaded bands are the 50th percentiles, and then the outer shaded bands are the 95th percentiles. And so the top graph here is showing the probability that we would detect at least one case. So this is how likely are we to identify that there's some level of H5N1 circulation happening. And in the baseline scenario, we find that detection is most likely through community testing and urgent care and emergency departments, with about a median 75% chance of detecting a case. Whereas in hospitals and ICUs, things are much lower. But we also find that all of these probabilities increase with disease severity across all of the healthcare settings because more people are presenting for care. But really the most drastic change is in the hospitals and the ICU settings, where we find that detection increases to essentially 100% in the most severe scenario. Then the second graph here is showing the total number of tests used per month in each setting. And this is where we actually start to see trade-offs. So although detection probabilities in the community setting were high, we find that we are conducting a lot of tests in order to reach that, with numbers that are unlikely to be feasible. And whereas the numbers in the healthcare settings are an order of magnitude smaller. You also might notice that the numbers don't change much with disease severity. And that's because they're really driven by the background activity of other respiratory infections. So when the number of H5N1 cases are at low incidence, there are many more people who are likely to be infected with seasonal flu or COVID and other things. And so that always dominates testing in these healthcare settings. Then in the third graph here, this is showing the number of H5 cases that are detected per 100,000 tests that are conducted. So like a measure of test efficiency. So these take into account the probabilities of detection, but also the number of tests that are needed to get to that point. And so here at baseline, we see that urgent care and emergency departments are the most efficient setting, but even hospitals and ICUs are more efficient than the community setting because of the huge number of tests that were needed in that setting. And then in the intermediate and the most severe scenarios, we find that hospitals and ICUs become the most efficient because more people are likely to require care in those settings. And then finally, the bottom graph here is showing the percentage of all H5N1 cases that are detected. And across settings and disease severity, we find that this is actually quite low. So we reach about a maximum of 15% in hospitals in the most severe scenario. And so this is really in contrast to the top graph, where, although we have a good chance of detecting at least one case, there may be a lot of cases that we still miss. But overall, what this shows is that really the symptom profile of the disease can have a large influence on detection probabilities in different settings, and will determine where testing efforts could be most efficiently targeted to pick up new cases. So I don't have time to go into the details here, but we did also look at other scenarios, such as what might happen if rates of testing declined in the summer months, when background activity of seasonal flu and general awareness about flu is lower. Not surprisingly, we find that this can substantially reduce detection probabilities. And so it's really important to maintain testing levels in periods of low seasonal influenza activity. But just kind of pulling together what I've gone through here. So in general, although we found that the percentage of all influenza or novel influenza cases detected was relatively low, we did find that the probabilities of detecting at least one case, so identifying that there is novel virus circulation happening, those were high in at least one setting across a range of different scenarios that we looked at, including disease severity, different testing assumptions, and also specimen forwarding assumptions. And so this is important because the detection of one case would facilitate the implementation of different public health actions, including things like increased testing, further virus characterization. And then in terms of what this means for pandemic planning, I think it shows, that there should be consideration should be made for strategies to rapidly increase testing in clinical settings once human-to-human spread of a novel virus has been identified or is likely. We find that the most efficient setting for detection will depend on the severity of the novel virus, and also that strategies should account for the possibility that many cases may not be detected even with high rates of testing. But with that, I'll stop there. Thank you for listening, and I'm happy to take questions here or via email as well.
Okay. Thank you, Sinead. That was really interesting work. So this wraps up our last talk in this first session about structural uncertainty, parametric uncertainty. I don't see a lot of questions in the chat, so I'm wondering if like people have questions to pose to the presenters. And yeah, and if not, Tom, if you have any thoughts to share or questions to ask, we can do that as well. And I would say if we are running a little behind on schedule, so if there's not a lot of energy because people are a little bit tired of so many presentations, maybe we can just take the break and then we can hold the discussion with the papers that are coming after the break. That's also an option. That sound good? Okay.
How long
Okay,
is the break, Pedro? 5 minutes or 10?
It's 5 minutes. Yeah,
5
I
minutes.
have a slide here with a time, but now that's not updated, so I'll push it to 45. So I think we're like 10 minutes behind schedule, but not too bad. Okay, so yeah, after this we come back with Eric and Laura on addressing inequity. So see you soon. Okay, so we are approaching the 12:45 mark, and we also see Eric there, and also Pedro, except that it's Laura, and she was losing my link, so I can rename you. But by the way, if you are one of the Pedro Nascimento de Lima with using my name, that's because you probably use the link that I forwarded to you. So you can fix that, but if you want, but if not, that's fine.
I fixed my name. Thanks, though. That's funny.
Yeah. Okay, so I see people are kind of sending a few questions in the chat, and see that Tom is already responding to them. We're a little bit behind schedule, 10 minutes specifically, so I think we can just go straight to the next talk. And so I'm very happy to introduce Eric Tatara. He is a senior engineer at Aragón National Laboratory, and his work that he's going to present focuses on modeling to improve health outcomes for people who use drugs, and that addresses uncertainties related to vulnerable populations. So this part of the discussion, the symposium, is about not only making health better on average for everyone, but addressing inequities, which is also a goal that we try to achieve with these methods. So Eric, the floor is yours.
Thanks, Pedro. I'm a researcher at UChicago and Aragón National Laboratory. The work presented here is actually a compilation of several different past and ongoing projects across a large group of collaborators at different institutions. It's these type of research projects require expertise across lots of domains. Otherwise, they wouldn't really be possible. And our funding is coming from a number of NIH grants looking at persons who use drugs and improving health outcomes amongst those populations. And we did the numerical experiments here at the Aragón computing clusters. So,
Eric,
yeah,
I think I'm going to share your slides.
I'm not sharing the slides at all.
No.
Oh, it was showing, and then something.
Yeah, they're showing up for me. It's there are two tabs, I think, Pedro.
Yeah, they
good.
Yeah, we can see them fine.
Okay, you see a full screen?
Go
All
ahead.
right.
Yeah.
All right. Okay. So the vulnerable populations that we're focusing on in this work are persons who use drugs. So that's a fairly broad category. One of the sort of main risks to this population is a high vulnerability to drug overdose, as people have probably seen in news reports that are ongoing daily. Is that the current hot topic is overdose mortality, number of overdoses due to fentanyl or other synthetic opioids, and the rates of that has increased dramatically in the last 20 years. Prior to that, it had been somewhat stable. The risks were among persons who use heroin or methadone, but since there is now a very large variability in the illicit drug supply, not just in heroin, but in everything now, there is a high risk of fentanyl. And if people are not used to exposure to that drug, they don't have a tolerance to it, and a very small amount of fentanyl can be fatal. So this is a current ongoing focus for overdose prevention. Lots of U.S. health policy centers are looking at these. In addition to overdose risks, a subset of persons who use drugs are persons who inject drugs. They inject with syringes, and often they don't have access to clean syringes, and therefore would engage in co-injecting behaviors with peers within their social network. So people will share syringes, and infected syringes or contaminated syringes are primary vectors for disease transmissions for things like HIV and hepatitis C or HCV. And HCV, number of cases has been going up again over the last 10 to 15 years. Number of active cases are going up in the United States. And HCV is a problem because primarily what happens through chronic untreated HCV is chronic liver disease, and then that means that people need, basically, you'll either have liver failure or need a liver transplant. So the leading causes for liver transplants are HCV, and the leading method of acquiring HCV is through drug use. So they are very pressing present public health concerns amongst this population. And so how we actually want to go about modeling these interventions is we typically define what we know about the model population using local population data when possible. The focus in these studies has been Chicago, Illinois, but this is a problem that's occurring throughout the United States and globally. And so we look at population factors, we look at those local contextual factors. So what are local rates of overdoses? What are local rates of disease? Is there criminal legal involvement? In other words, are people who tend to be using illicit drugs have a high probability of being arrested and incarcerated for that. And that adds complications in identifying and treating these individuals and providing them care that we need. So there's a disparity there between your people who need care in a community setting versus people who need care that have criminal legal involvement. Those local contextual factors are often very difficult to define quantitatively with very fine point estimates. And so we will look at what are reasonable bounds for some of these in terms of modeling the effects on what our outcomes are. And so the outcomes are, we want to reduce overdose deaths, we want to reduce behaviors that would lead to more drug use behaviors, will lead to more infections and overdose. In addition to those contextual factors, which are difficult to concretely quantify, institutional factors, which are the type of things that we're trying to model as sort of levers in this simulation, and that can be tied to a policy space. So are individuals waiting too long for a health screening to get treatment, or are individuals being identified at all? If you've got a large population of local populations of persons who use drugs, and some of whom are carriers of HCV, are you able to find these people, enroll them in a treatment, get them to stay on treatment, and then continue doing that with such intensity as to essentially address the problem, right? And so essentially, we've got so many parameters in a potential model. We use sensitivity analysis as one of the tools to sort of first identify which parameters have the largest impact in terms of the model input parameters on the model outputs. And so this type of visualization here is a tool that we use where we do sensitivity analysis. It basically highlights model input parameters that contribute the largest to the model outputs. So we would identify those first, and then do more comprehensive numerical simulation studies by only focusing on those model inputs that have the greatest contribution to output. Because if you don't do these sort of initial screening and focusing on which parameters are the most important, then the parameter space simply gets numerically infeasible to essentially iterate through the whole set with any fine resolution. And so the two sort of studies that we've looked at, these were published recently in PLOS One and PLOS Computational Biology, are elimination of HCV in people who use drugs. So even though HCV, if left untreated chronically, can be fatal, there are antiviral medications that, if provided to persons with HCV, it has a very high treatment success. That's assuming that the person is adherent to the medication. And so that adherence to medication is an uncertainty in the model. So we looked at a couple different ranges for treatment adherence amongst these individuals. And then we looked at spatial inequity in terms of access to medications for treating opioid use disorder. And so there's sort of two complementary approaches here in terms of improving health outcomes. One is identifying infected people and treating them so that they're no longer infected, and so that they also cannot reinfect other people in this network here of syringe sharing users in Chicago. And then another aspect of that is if you can provide medication for opioid use disorder that reduces the individual's cravings for opioids and reduces their number of, say, drug sharing or syringe sharing episodes over time, reduces their risk of both of overdose and of transmitting HCV. And so we looked at a couple of different modeling scenarios where we wanted to say, starting from a baseline scenario where we don't provide treatment for HCV, what types of reductions in incidence in new chronic infections over a 20-year period can we achieve? So starting from the pretreatment, these graphs are showing reduction in new chronic infections. One would be essentially same as pretreatment, with an increase would be increase in infections due to treatment, and reduction would be reduction in HCV incidence due to the different treatment intensities. And the colored lines here are showing simulated percentages of enrollment of the total population. So from 2, 5, 7.5, and 10% of the total population enrolled annually, what type of timelines can be achieved in terms of reducing HCV. And the goal was to get it below this dashed line here, which is showing a 90% reduction in HCV from the baseline, which is a World Health Organization goal. They want to try to get, a 90% reduction from baseline. And so different levels of adherence results in different outcomes. When you have low adherence and you limit treatments, lifetime treatments between 1 and 3, these goals are not actually feasible. Even with high levels of enrollment in antivirals, the HCV incidence kind of plateaus. It never goes below, like 0.25% or so from relative to the pretreatment levels. And so it's showing in these situations, if we have a fixed limitation on treatments per individual per lifetime, you need a very high level of adherence over many years in order to achieve elimination of HCV in this population. A different alternative is if you don't limit restrictions on treatment, if you just let people have an unlimited number of treatments, in that case, the adherence is less important, because even with low 60% adherence, meaning 60% of the people will be adherent to the medication and 30% would not. They would not successfully complete the treatment and be cured. Under those very sort of conservative estimates, even a 7.5% of the population, if they're enrolled annually in antiviral treatments, you can eliminate HCV in that population. And the uncertainty in this comes from the fact that if you look at the histogram distribution of how many times everyone is treated within a certain simulation, about 80% of the people or more only require a couple of treatments, but there's a small number of individuals that require many, many treatments over a lifetime in order to cure them, because they keep getting reinfected due to the drug use behaviors, getting reinfected from other individuals in their syringe sharing peer network, who then, the circulation of infection is basically just uncontrolled unless you're able to identify and enroll these small numbers of individuals and treat them. And so that's suggesting that in these prior graphs, pulling down the HCV infection incident is very sensitive to making sure that there aren't essentially people who are hosting the disease in the model population, and it just provides a vector for reinfection that cannot be controlled. And another interesting question was, if we're able to actually achieve elimination over a 10-year treatment period, where we have this very high intensity effort for recruiting and enrolling people in antiviral treatment. What happens if we stop enrolling treatment after it's achieved, or what happens if the intensity of the treatment enrollment is reduced? Why that would happen would be limitations on resources or change in focus. If policymakers and people in government-funded programs see that HCV is no longer a problem, what happens is they're going to potentially cut funding for programs or divert focus to somewhere else. So we ran the simulation for 10 years with a high level of treatment. We achieve elimination at between year 9 and 10. And then we said, okay, we're going to reduce the enrollment of people down to 0%. And if you do that, what happens is within 5 or 6 years, you just go back up to the baseline. So there are small numbers of infected individuals or people coming in from other geographic regions into the local population with HCV, and then it spreads very quickly because this network is very highly connected, and everyone is susceptible to reinfection after they've been treated for HCV. And so the simulations are showing that values of 0.5% of the population, or in our case for Chicago, since the total population was 32,000, this is about 160 people treated annually. So that's the target enrollment intensity that's really needed to keep it, to keep the elimination goal met. Simulations of enrollments that were smaller than that, between 32 and 64, again, total individuals in the Chicago area treated, shows that what happens is it does go back up. It just more slowly depending on the level of intensity there. So somewhere between 0.2% and 0.5% is really the goal here. And to be conservative, we would probably say 0.5% or greater is required to meet that goal. And so one of the main conclusions of this work is that since this elimination goal is difficult to achieve given the uncertainties of individual persons' adherence and behavior, and effectiveness of identifying infected individuals and treating them, combining this with other intervention strategies such as harm reduction is important. And so harm reduction can include providing clean syringes to people. HCV vaccines, there is currently not a vaccine for HCV, but that's something that's being studied now. So a vaccine to prevent infection, or other treatment programs such as medications for opioid use disorder. So if you can sort of get ahead of the vector for infection, which is sharing syringes, and reduce the probability of that happen, then that helps even further. And so that was a follow-up study to that. What we did is we wanted to look at barriers to access in medications for opioid use disorder. And so there are a couple of different medications for this. Methadone is one of them. And so that's a medication that people with opioid use disorder would obtain through a medical provider clinic. And so they have to go through a screening process, see a physician or other health providers, and then go to have the medications refilled on a regular basis, along with reevaluation every couple of days, 2 weeks. And so the focus of this particular analysis was we wanted to say, what does the actual distributions of methadone providers in Chicago look like? So these are the dots on this map on the far left. This data was obtained from state of Illinois, maintains a database for all providers of MOUDs to people. So we looked at the actual distribution, and then we fixed the number of providers in this study. I think it was around 80 or so. I said, what happens if you spatially randomly distribute them in the area? What are the effects on access to each of the zip codes, and the zip codes in these maps are actually so small it's hard to see, and the larger boundaries here are counties. But basically what happens is if you just randomly scatter these, then access to areas that have very high population density, which is the city of Chicago here, is this the county right next to the lake, right? This has the highest population density, followed by the collar counties. And so it turns out that the actual spatial distribution was done intentionally with purpose, right? They put them where there's a high population density and there are less providers located in the suburban counties. So that was just essentially to see what happens relative to the actual case, and then compared it to additional scenarios for geographic access. So need-based one, we relocated them closest to zip codes that have the highest adult population density. So we see it like, most of them here moved into the Chicago because this is where all of the population density is in the area. And then need-based two is population density of persons who inject drugs. So it's similar to this, but not exactly the same. And across the four different scenarios, this visual analysis is showing access. So the dark blue areas are zip codes that are classified as having spatial access, meaning there's a certain distance threshold that people in that zip code are, within some certain distance to the provider, and then the light brown areas are not accessible. And so going from the actual to the two need-based, you see different shifts in patterns between suburb and urban access. This provides a pretty high level overview, but doesn't give you really. So what we wanted to look at in terms of the quantitative takeaways, what does this do to actually impact the syringe sharing behaviors? And so we ran many different simulations combining the geographic access scenarios with assumptions about how we thought people want to travel, how far people want to travel to access these medications. And so from literature on travel distance barriers, it suggests that people quite clearly prefer short distances when they're in urban environments. If you've got access to public transportation and you only have to go a mile, it's a lot easier than if you had to drive 5 miles away. If you don't have access to transportation, it's either difficult or impossible. So we looked at 1 mile and 5 mile non-urban, which are these orange dots, and then we kind of had a medium travel distance threshold, which are the blue dots, and then a far distance travel assumptions, which are the green dots, meaning the people with low access travel assumptions would prefer not to, or in fact, not actually travel it to those providers if the distance was too high. And so what we looked at is, for each of these simulations, what is sort of the net reduction in syringe sharing behaviors over a year for the model population? And in order to condense all of these simulation results into something that was sort of easier to digest, visually, we made this graph of regret score. And a regret score is basically across the 4 different scenarios, actual, random, and the 2 need-based, which of them performed the best at reducing syringe sharing behaviors. So the values of 0 are the best. So that means essentially that across the 4 scenarios, the need-based one, where we put the methadone providers closest to the adult population density, worked best when people were willing to travel sort of medium and far distances, but not as well when people were only able to travel very short distances. And so that is basically suggesting that this is important because the local population density of drug users is sort of not not represented well just by looking at the adult population in total. And so the actual distribution of providers does fairly well when you consider that, you know, people are willing to drive, you know, farther to access a provider. What we really wanted to do was which of these 4 scenarios works best when considering all of these different assumptions, because we don't actually know which of the assumptions corresponds to all individuals in all of the geographic areas that were studied. And so we just use a 75 percentile, you know, we did a box plot and use 75 percentile essentially as the metric of which scenario performs best. And across all of the 4 scenarios, the need-based 2, in other words, putting methadone providers where you have the highest population density of injectors, people who inject drugs, it essentially provides the best reduction in syringe sharing across the 3 different access assumptions. So since we don't know, you know, we're saying essentially that provides the best the best results. So one of the takeaways from that is, even though you're able to provide, you know, better access locally to density, you're also moving access away from suburban locations, because what we did is we kept, you know, we fixed in this analysis the number of providers, we just shifted them around geographically. And so, you know, this makes a case for, you know, simply moving providers or reducing barriers to access in itself isn't necessarily a policy objective. You know, you need to potentially remove barriers to access and, you know, increase the number of providers. And since we can't actually observe behaviors in the model population to know what the actual travel preferences are, you know, we didn't do essentially an optimal intervention in this case. And so we decided that, you know, this robust intervention, which was this need-based 2, it provides, you know, the best outcome in syringe sharing given the various uncertainties amongst the travel distance preferences. So I think I'm at time there, unless I've got more. Pedro, so did I go over, or do I have more time?
Yeah, I think we're about at time. Yeah. So yeah. Thanks, Eric. Really good presentation. Really interesting, detailed intervention. So yeah, thanks for that.
Sure thing.
So we have about 48 minutes left and 3 presentations left. So we're not completely out of time. So, but yeah, gotta just keep moving a little bit. And now we have Dr. Laura Matrajt. She's a staff scientist from the Vaccine and Infectious Disease Division at Fred Hutch. And she will talk about addressing uncertainty and equity trade-offs in vaccine allocation policy. Yeah, so Laura, you can take it away.
Sorry about that. I couldn't take out the mute off. Okay, thank you. So I'm gonna talk about why I cannot take this out. Sorry. Anyway, I'm gonna talk about vaccine allocation in the context of COVID-19, and I'm gonna present two things that I did. The first one was done in I started doing this in May 2020. And I wanna remind you how we were back in May 2020. There wasn't a vaccine. The clinical trials haven't even started yet, but I knew this was going to be the best tool to control the pandemic. And I also knew, because of my previous experience with COVID, that with influenza, and that there was going to be shortages of vaccine. And so there was this urgent need to come up with a vaccine prioritization rationale. And so what we did is we used mathematical models and optimization algorithms to answer this question: who should get prioritized to get the COVID-19 vaccines first? And so this is work that I did with my collaborators. You can see them here. I'm sorry, it's annoying that I cannot take this thing out. There.
Yeah, it
Ah.
is annoying, but we can see
I'm so sorry. Okay. So now, so again, I want to remind you everything we didn't know back in 2020 in May. We didn't know if we were going to have vaccine. We didn't know how efficacious it was going to be and how many doses we were going to have and when. Also, there was a lot of things about the natural history of COVID-19 that we were unsure about. And there were different countries were managing the pandemic in different ways. And so even though I don't have all the theoretical background of deep uncertainty, I knew that I wanted to make minimal assumptions, that I wanted to be as conservative as possible, and that it was very important to explore a vast range of assumptions because I wanted this to be able to hold in many places at many different times. And so I did just that. So I want to talk to you a little bit about how I did that. So there were 5 vaccination groups, and the first big uncertainty was vaccine efficacy. So I consider vaccine ranging from 10% to 100% efficacious. And I knew different countries were going to have different coverages. So I wanted to play with all the numbers. So I consider vaccine coverage enough to vaccinate 10 to 100% of the population. I also knew that at different stages, you would be interested in minimizing different things. So I consider 4 different metrics of disease burden: symptomatic infections, deaths, maximum number of non-ICU and ICU hospitalizations, and these 2 were a proxy for healthcare burden. And so I want to quickly show you the results. So this is a very busy slide, but I want to bear with me. So each little square here represents a different vaccine efficacy, ranging from 10% on the top left to 100% on the right, on the bottom right. And each little row represents having a different total vaccine coverage available. And the different columns represent the different age groups to vaccinate, and the colors, what percentage of that age group to vaccinate. So if you look at the square on red that I marked there, that is telling me if my vaccine was 40% efficacious and I had just enough vaccine to cover 10% of the population, then the optimal thing to do, if you want to minimize deaths, would be to vaccinate all of the people in the group of 75 plus and use the remainder of the vaccine in the 65 to 75. And although this looks very complicated, if you just take one step back and look at the top row, it's all telling the same story. And what it's telling you is that for vaccine that has low vaccine efficacy, it's the best strategy is always to start vaccinating the older adults that are the high-risk groups. But if you have a vaccine that is more efficacious, so that the vaccine efficacy is 60% or over, then there's this threshold where for low coverage, it's the same thing. You start vaccinating older adults, and as you have more vaccine, you go down in the age groups. But if you have a ton of vaccine, so if you have enough to cover 60% of your population, then you switch to vaccinating those who are the high transmission groups, the children and young adults. Okay, and so I wanted to make sure that when I said this was true for a wide variety of assumptions, and there were so many uncertainties. So I did 2 things. The first one was robustness of the optimal vaccination strategies. So I reran the optimization and changing the parameters that I thought were the most important. And that was the number of infections, the number of initial infections, the proportion of the population that has previously been infected, which we didn't know at the time. And I actually took 20%. It ended up being way less than that. But I took 10, 30, or 40%. And the susceptibility of children to infection, because at that time there were a lot of reports that children were not as susceptible, but I didn't think that was the case. And then I also wanted to, and then I reran the optimization for all these possible combinations of BE and vaccination coverage. So that's 100 combinations for each combination of these parameters that we were very uncertain about. The R0, which represents the transmissibility of the disease, the percentage of asymptomatic infections, the relative infectiousness of those asymptomatic infections, and the relative infectiousness of the pre-symptomatic infections. And so when you do the math, those are 36 possible combinations that I ran for these 100 pairs of vaccination coverage and vaccination and vaccine efficacy. And then for the main analysis, I wanted to have a sense of how sensible the results were to the other parameters of the model and how far up or down deaths or infections were going to be. I wanted to provide some sort of bounds. And so for each of these parameters that I listed here, I ran combinations of 1,000 parameter sets and ran them all, using particular distributions for each of these parameters. And then I thought I was done, and I had done a ton of sensitivity analysis, but the reviewers didn't think so, and they wanted me to do additional robustness analysis to these other parameters: susceptibility of developing symptoms, additional basic reproduction numbers, assuming different distributions of pre-existing immunity, and the duration of incubation period. None of these or the other things that I showed you before changed. And so when I did my conclusions, I was pretty certain that of these, what I'm gonna say, that and at the time we thought the virus was pretty stable, and the results show that the pandemic could be controlled with a vaccine as long as it was at least 50% efficacious. I also show that over half of the deaths could be prevented with only 35% of the population if you were willing to optimally vaccinate them. And this trade-off that I told you, that if vaccine efficacy was 60% or over, it's better to vaccinate the high-risk groups with low coverage, but with high coverage, you want to switch to high transmission groups. And I also showed that if you wanted to different objective functions, so depending what you wanted to do, you needed to do different things. So if you want to control transmission, you want to give the vaccine to the high transmission groups. But if you want to prevent deaths, you needed to protect the high risk group. Okay, and so this received a ton of media coverage, but more importantly, it was used in the WHO roadmap for prioritizing the use of COVID-19 vaccines. And one thing that came over and over again, every time I gave a presentation or I talked to the press, it was always like, why you didn't include anything about race? It was pretty obvious that race was being a big thing during the pandemic, and that the pandemic was not being felt equally in all the different racial ethnic groups. And my answer back in 2020 was because I don't have the data. But as the data emerged, I was able to do a retrospective analysis. And this time I wanted to consider equity in the optimization for COVID-19 vaccine allocation. And so this is a group that was basically done by Erin Stafford, who was a student back then at the University of Washington, and it's published in PNAS Nexus. And so this is the situation in Oregon, but and I'm showing Oregon just because we had data from Oregon, but it was pretty much the same all over the US. And so what this is showing the mortality rates of people of color, which I'm gonna refer as BIPOC, compared to the white population. And so, for example, the way to read this is that people of color aged 50 to 59 were almost 6 times more likely to die compared to a white person in the same age group. So the dilemma is, who should we have vaccinated? The older, who are mostly white, more accessible population, and who are most at risk of severe disease or death, or the younger, marginalized populations that face the most inequities and are at increased risk of acquisition. And this was a dilemma that was playing in early 2021. And so the question is, could we have administered the vaccines in a more equitable way? And so I wanna before I move on, I wanna say that this is extremely difficult to take these decisions in the midst of a pandemic. There are intrinsic trade-offs that policymakers need to consider. Inequity is a very complex problem. And obviously, I'm not pretending to claim that any mathematical model or optimization or either vaccines can solve the inequity problem in the US. But what we wanted to do was to provide a quantitative framework so we can better understand inequity in public health interventions, and we can start to address this inequity. So the first big question was, how do we address inequity in terms of mathematical terms? And there's uncertainty about that because intuitively, you want these bars to be equal. So you want the light purple to become ones. But there's a lot of ways to represent that mathematically. So I'm just putting here the 5 formulas that we came up with after thinking and trying and testing a lot of things. And we wanted to see how different the results would be with each of these formulas. And so we did 3 things. We minimized mortality only, or years of life lost, and we minimize inequity only with one of the 5 measures that I just showed you, and we also minimize both at the same time with the hope of finding a happy medium where you can minimize health burden and inequity burden at the same time. And so this is it was just a standard LDE model with 5 age groups as before, but we included race and ethnicity both in the risk of acquisition, in the risk of disease progression, and also we had race stratified contacts at home and work. And so I'm not gonna show you all the results because we're running out of time, but this is when we assumed that we had enough coverage to vaccinate 10% of the population. And so the bars to the right in the dark purple means the proportion of whatever is on the row averted. So that's deaths averted always, and the light purple is inequity averted. And then what each row tells you when you minimize each of those metrics that I told you about. And this is when you're minimizing 2 things at the same time. So, not 2. So you minimize deaths or inequity in deaths or deaths and inequity. So that, and same thing for years of life lost. And so what you want to find a happy medium is for these bars to be the biggest possible and the similar possible to each other. And so at low coverage, minimizing a single measure alone leads to a big imbalance. But then as coverage increases, it is possible to minimize both measures simultaneously. But more important, but also, I talked to you about all these metrics that we tried. And when we plot all these metrics and we compared how they did with respect to the other metrics, you have them all here in this plot, and you cannot really distinguish them because they perform equally well. And so this was very good news because it meant that it really didn't matter which measure of inequity you choose. They were doing kind of the same job. And with that, I just want to jump to the conclusions. So with low vaccine supply, minimizing deaths was the optimal way to preventing overall deaths. And it prevented more deaths in the marginalized communities, even if there was more inequity. With low vaccine supply, then there's this trade-off between being more equitable and protecting overall mortality. And this is true only because COVID-19 is so concentrated in the oldest population. So it wouldn't be the case for HIV or for Mpox, for example. And so when we minimize both, we were able to achieve more balanced allocations with higher equity, and but in turn, a small reduction in small deaths averted. And as you have more vaccine supply, it is actually possible to have them both, to minimize mortality and inequity at the same time. And with that, I want to thank you all.
Okay, thank you, Laura, for the presentation. I think it was a really good presentation of, working towards minimizing inequity from health outcomes. We're running a little bit short on time, so I think we can probably go ahead with the next 2 presentations. And then if you have questions about this talk or the following talks, you can write on the chat, and then hopefully at the end we have a little time to discuss. So now I would like to hand over to Crystal Watson. She is the Deputy Director of the Center for Outbreak Response Innovation and a Senior Scholar at Johns Hopkins Center for Health Security. And she'll share some of her work on improving decision-making and deep uncertainty of novel infectious disease emergencies. So yeah, Crystal, you can take it away.
Okay, thanks so much, Pedro. Can you see my screen? Does that? Nope.
Yes, we can. We can see a lovely view, which is not what.
Not what, yeah. How's that?
Okay, there.
Okay, wonderful. Thank you so much. Okay, well, thank you again for the invitation. It has been a really interesting and instructive day. I loved hearing about the other work going on in this space, especially the last presentation. Thank you so much. That was great. And I think that transitions well into what I want to talk about, which is more at the implementation and policy level. So I've been working in preparedness and response to infectious disease emergencies since 2004 with the Center for Health Security, now at Johns Hopkins. I actually focused my doctoral dissertation on decision-making during public health emergencies, particularly involving environmental contamination. And this work led me to DMDU literature, and I actually got to attend the annual meeting in Oxford in, I think, 2017, if I'm remembering right. So it's really nice to be involved with this today. A lot of my work at Johns Hopkins was diverted into COVID-19 response, but I always come back to how we can more systematically support decision-making in preparedness and response. So I'll give you a little bit more in detail in a minute about this organization that I'm representing today, but I have been over the last year a new deputy director of this center at Johns Hopkins called the Center for Outbreak Response Innovation, or CORI. And we're funded by a large cooperative agreement from the Center for Forecasting and Outbreak Analytics from the CDC. So this work has brought me back to decision-making and decision support in a new way, which is exciting. So I'll just talk to you briefly about the problem we're trying to address, talk a little bit about CORI and our mission, and then a little bit about our initiatives. But I'll try to keep it brief because I know we're running behind. So this should look familiar from Robert Lempert's initial presentation. So we're really focused on infectious disease emergencies, outbreaks, and decision-making. And my particular interest is in this really rapid response and decision-making to mitigate impact on public health of an emerging event. We know that decision-making in these emergencies is highly complicated by urgency, uncertainty, and complexity. And I think we're often in the realm of the unordered or maybe more chaotic, sometimes more ordered depending on the outbreak. But I think in that upper left-hand quadrant is where we often end up. So one thing that we've noted is that during these types of emergencies, responsibility for decisions often elevates to the political level. And these are political leaders who may not be adequately prepared to make public health decisions, but they are facing a lack of scientific evidence. The data that they do have has to be considered alongside political, ethical, legal, logistical, economic, and other factors. And there's very little in the way of training or guidance for these types of leaders how to make crisis decisions. So we know a lot of work has been done on decision-making for other types of crises, especially by RAN. And one thing I often think about is the nuclear space, but this is much less well-developed for public health. And we know public health is fairly disorganized as in the aggregate, very mixed in strength and effectiveness, and federated, underfunded. And so the quality of decisions within public health as well as within political leadership is highly variable. So I do think this early infectious disease crisis situation really does meet the DMDU definition. So while our organization isn't using DMDU methods explicitly, at least not yet, we've been exploring how we can make these decisions more robust in these crisis situations. So we found that there is really a critical gap in the ability for leaders to routinely make these decisions under extreme uncertainty. So we are focused on this in order to increase the fidelity of these decisions. So just a little bit more about our center, Corey. We are an academic center at the Bloomberg School of Public Health, Johns Hopkins. We're members of the CDC Insight Net, which was formed through CFA. And our expertise is in outbreaks communication and supporting public health practice. There are 3 types of centers that are involved in this network of centers through CFA. There are innovation centers, which work to build models, integration centers, which test and integrate models into public health, and implementation centers, who are there to bring models, analytics, and other tools to scale across the country. So our center, Corey, is one of 3 implementation centers, and we're at the end of this InsightNet pipeline. So our job is to take these innovations that have been built and piloted and tested in 1 or 2 locations and figure out how to implement them at scale throughout the country. So while this pipeline matures, our center is focused on working with partners in public health, industry, and communications to prepare to be able to use modeling and analytic tools, and to build a network of partners and an infrastructure, both to implement the tools widely and collect data that can feed back into innovation and integration centers to inform and improve model development. One pillar of our cooperative agreement is explicitly working to improve decision-making resources for state political leaders. So we're currently collaborating with the National Governors Association, and I can talk a little bit more about that in a second. One challenge we've found with our work so far is that our partners in public health in particular are not necessarily ready for, and this is variable across the country, but I think at a high level, not ready for or necessarily bought into the value of more advanced modeling and analytics for the work that they're doing every day. So we are also finding that at the end of this InsightNet pipeline, they're not necessarily models that are ready for prime time and scaling to support decision-making widely across the country. So to navigate some of these challenges, we've come up with what we call the Corey flywheel, which is what you see here. You move clockwise around the wheel, each time increasing the strength and complexity of the work. So we start with what we've been doing over the last year, which is offering some evidence-based resources to our partners, getting them involved in our network. This helps us build trust with them and then recruit partners to participate in what we're calling our evidence generation network. And then we seek to grow the evidence base and generate more resources and tools through InsightNet that can move the flywheel around again. During our first year of work, we've been focusing on the initial third of the flywheel, but as we move forward, we're going to build the infrastructure to engage on innovative approaches coming out of the network. So for example, we are working in the next year to enroll public health partners in an evidence generation network where we can essentially run what are akin to clinical trials for public health outbreak innovations. We're also focusing on the concept of high reliability and trying to understand what steps it would take to turn outbreak response and public health more broadly into more of a high reliability organization, something more akin to the FAA or NASA. So one thing we've been doing over the last year is conducting needs assessments with our partners. We're starting with our state health departments and our governors. So we're really trying to understand what gaps and needs are in information for decision-making during these infectious disease emergencies. So this is the project that I'm very focused on, is partnering with the National Governors Association to engage governors and eventually introduce them to better data modeling and forecasting and analytics in order to improve their decision-making during health emergencies. And so we have developed this needs assessment instrument. We've conducted interviews and trying to understand that. We're building some basic tools to support the process of decision-making for governors. And then in the next year, and you can see here are some of the some quotes from governors' offices that we've seen showing that they are interested in the value that some of these decision support tools and models could provide. So we are building that kind of interest as we go as well. And then in the next year, we are hoping to partner even more closely with NGA to participate in a boot camp for new governors, to create a public health outbreak response policy academy, which will provide opportunities to partner closely with governors' offices to test and refine models aimed at policymakers, and then continue to build support for a broader consortium of governors that might participate in tabletop exercises that we have done in the past or scenario-driven planning to test some of the tools that are being developed. So I say all of this because I am really interested, we're interested in partnering broadly. And so interested in taking some of the tools that are being developed in the DMDU world and hopefully applying some of these methods back into scaling modeling and decision support for elected leaders. We are also partnering with large employers, and we're also considering individuals, so the general public, as decision makers as well. So there's lots of area for work to be done here, and so definitely wanted to present what we're doing and give you my contact information in case there are areas where you are interested in partnering. So with that, Pedro, I think I'll stop, and thanks very much.
Yeah, thank you, Crystal. Yeah, really interesting to see your work kind of pushing tools and improving analytics in the real world. Now, last but not least, we have Dr. Tomás Aragón. He's the State Public Health Officer and Director of the California Department of Public Health, and also an Assistant Adjunct Professor of Epidemiology at UC Berkeley. And yeah, I'm very excited to have him present this final talk. He will talk about California's Department of Public Health Decision Intelligence Unit. So yeah, Tomás, you can take it away.
Okay, thank you. Pedro, can you hear me?
Yes, we can.
Okay, fantastic. And I had to step away for an hour, but I've been enjoying this tremendously. So I'm going to give you a little bit of an idea of what's happening in California. I'm going to move relatively fast just because I know there's not a lot of time. And I'm going to start with a story. And the story is on March 15th. I was a health officer of San Francisco. I was woken up by the director of public health, who is my boss, the agency boss above me, and says, Tomás, we've tried everything. What else can we do around preventing COVID? And I said, well, there's two things we haven't done. We haven't done universal masking or shelter-in-place order. And at this time, there was no place in the United States where a shelter-in-place order had taken place. So we quickly got together the health officers for the 7 local health jurisdictions representing the Bay Area of 7.6 million people. And we decided in a few hours to basically shut down the whole Bay Area. And we had to mobilize legal counsel, notify elected officials, and by 12 noon the next day, all the orders were issued. And at 12 midnight that evening, the Bay Area was shut down. That was on March 16th. We were the first place in the United States to do this. And 3 days later, the state did a shelter in place, and then New York City approximately a week later. All of this happened very fast. And I think that's one of the challenges I want to emphasize to folks here is that we move at a speed that's much faster than the academicians can help us. And so I'm going to give you some examples. I think I'm beginning to appreciate that the DMDU is the overall approach to use, but it has to happen fast. And in order to happen fast, you have to iterate with us and sit in on these meetings. And I'm going to talk about just what we did this weekend with detecting H5N1 in raw milk in Santa Clara County. These things happened, we're notified, and we have to literally within 24 to 48 hours come up with big decisions that impact a lot of folks. So I'm going to share with you some of the things that we learned. I'm calling this, I call it decision intelligence. Part of the reason I call this decision intelligence is because I want to get people to think close to emotional intelligence, sort of common sense approaches. Now here's the definition from the former chief decision scientist at Google. Decision intelligence is about giving yourself the skills and tools to turn information, whether it's your memories of lunch conversations or it's your foray through a massive database, into better actions at any scale and in any setting. So the idea is to get this down to some key concepts that can be implemented really quickly. And then of course, if you have the time and expertise to go ahead and fill in the information with modeling and all these other great tools that people have. And so this is now the sort of the framework that I've been promoting. At the end of the day, and I now call it human decision intelligence, because the term decision intelligence is going to be gravitating more towards using machine learning, artificial intelligence, more computational approaches. And I think you have to really understand the human process of decision making in teams first, iterate around it, build off that. So it has to be team centered, sort of like human centered design, human team centered design processes that operate very fast. And how do you build out and activate different components if you have the time and expertise? So we have to start with problem solving. What problems are we working on? We have continuous improvement. We have to incorporate ethics, science, and technology. And I put over there decision-making under deep uncertainty. I'm coming to recognize that that's really the overarching framework that's easier to deploy. I have some definitions there that you can look at when you get the slides. Other thing I want to point out is, you know, I've been reading Cass Sustein's books on decision making, and he approaches it primarily from a policy making perspective, but he has this concept of what he calls first order decisions and second order decisions. First order decisions are the decisions that you make in the moment. Second order decisions is when you have time to develop standards or rules of how decisions should be made if certain things happen. And that's been really helpful to me to sort of recognize where we're at. Like this weekend was a bunch of first order decisions. Ideally, we would have done some exercises and have come up with some rules where we would have made decisions much more quickly. So this is a table from his book that sort of talks about the different approaches that people take to decision making, depending on the burden of the decision making on the spot and the burden of the decision making beforehand, where you have time to sort of figure this out. Okay, I'm going to quickly show you some types of decision that we make here in public health. I already mentioned the COVID example. And so the first thing we do is actually think really to have a basic framework for problem solving. So this is a basic framework that we promote for problem solving. Is you have to find the right problem. You have to define it carefully. So with COVID, and this is actually the mental model I put together. I did this by hand. I developed a one-page sheet early on in the pandemic, and that was like my playbook. Imagine you're watching this, when you watch football games, you see the coach that has their one-handed thing, one pager. I had a one-pager based on this model that sort of had all the different things that we were doing, and it helped me to explain what we were doing to folks. Defining the problem. So with COVID, we focused on transmission in the community. That was the problem. If I were a CEO of a hospital, it would be the problem would be, do I have the staff and resources to take care of patients in the hospital, including in the ICU? So how you define the problem is really important. What are the consequences? That helps you prioritize the problems. And then what are the underlying causes? Because you have to develop countermeasures. And so that's the general approach that we use. And we did publish an article summarizing what we did on March 15th and 16th and how these concepts were applied. Although it was really retrospective that I organized this information, but that's what I carry in my head. The other thing in terms of public policy decisions, so I'm going to give you a quick example, is that a few days ago, we were notified that Santa Clara County, through their testing of retail raw milk, they identified H5 influenza A in raw milk. That was the issue that was presented to us. And so now we had to then work with the California Department of Farms and Agriculture to decide what we were going to do. A lot of stuff happened over the past few days because we had to deal with legal authority, how to implement legal authority, the testing, chain of custody, confirmation of the test. So it was sent to UC Davis lab that does all the testing for agricultural samples in California. As you know, there's an ongoing outbreak of H5N1 in not just poultry from the birds, but also now in cattle. And so the dairy cattle are the ones that are most impacted in California. And, and we do have 6 farms that produce raw milk. So after sort of getting all that information together and coming up with options, we then had to get input, not just from different levels of legal authority, but also from our elected officials, because we serve under the governor, as the previous speaker was talking about. Because at the end of the day, it's really the governor that's going to, the governor or his or her team that's going to make these final decisions. This here on the left-hand side are sort of the kinds of options that are available to us. You see their guidelines. Coercion would be something like mandatory testing, regulations, legislation. So these are sort of the different levers that we can pull. And at the end of the day, we're trying to influence behavior. And so that's the green circle in the middle. This comes from implementation science. And I would argue that everything that we do in public health is really about implementation science. And at the end of the day, it's about influencing behaviors of institutions, communities, and people. So I mentioned H5N1. This is just an example of the one of the issues we have to deal with is cannabis regulation. When cannabis was first being introduced here into the state, whether you focus on decriminalization all the way to commercialization. So what happened in California is that it ended up focusing on commercialization with some regulation, and big complicated field. This one moves much slower. This is not the one that moves in a matter of hours to days, but it moves in a matter of weeks to months to years where these issues come up. I do want to mention one more thing. Actually, I'll mention it as I go through these other decisions. So the framework that I've carried in my mind that I've used is this decision quality framework that you may be familiar with. And you can see it at decisioneducation.org. There's also a book called Decision Quality that goes into this. And this is what I learned when I did my decision analysis certification at Stanford several years ago. And I take this six-step approach, and that I've arranged it into this framework that I'm showing you right now, is sort of framing the problem, who's sitting at the table, what are we trying to accomplish, and then sort of working within here, what information is available to us across this whole system of decision making. What are the alternatives available to us? What reasoning process are we going to use? Commitment means at the implementation stage, you want to involve the right people who are going to implement this. So the earliest you include them in the decision making. And it always starts with looking down the line. What are we trying to accomplish? And what are the consequences of the actions we take? So this is the general framework that I've been using. And this framework facilitates decision analysis. And the other thing that I think about when I think about stakeholders, I developed this checklist. I call it the help to checklist. And that is when you're thinking about a problem, thinking about what are the health outcomes you're trying to impact, health equity concerns, ethical issues, efficiency issues, legal issues, logistical issues, public trust, and political support. So in my mind, when I'm thinking about this, I'm always thinking about all these different things, and public trust and political support is really, and legal is really important. So with this H5N1 in raw milk, we had all of these things in the front of our minds. Now, this type of framework is easier. Actually, I'm still in this concept of information. This is stuff that folks already know, because this gets to the issue of deep uncertainty. Basically, what do you know? And then in terms of decision makers, how much awareness do they have in terms of what they don't know and what they don't know? So this is things that you folks have been exposed to, but it's really important because we have blind spots. So you want to be focusing in your deliberations on revealing information, getting your blind spots, asking people to help you. This type of approach also facilitates decision analysis. And the example here that we did it retrospect, we did it, but we didn't do it in a very rigorous, we didn't do it as rigorous way, is when we had Mpox introduced. We had the outbreak in California. We had live vaccinia virus that was available through the vaccine called ACAM 2000, and then attenuated virus, which was available through Jynneos. The ACAM 2000, higher injury rate. The Jynneos was in short supply, and the CDC was making ACAM 2000 available to us. There was enough information to do a straightforward decision analysis on this problem, but we did not have the wheels oiled to be able to do this as quickly as we could have. CDC did some analysis. We did some independent analysis. We converged towards the correct answer, which was do not use ACAM 2000 for Mpox, because the people most impacted are HIV positive and are most likely to have adverse outcomes. This analysis, in my opinion, took too long. It could have been done much shorter if we had been practicing and iterating on these types of problems. So this was an example where good old off-the-shelf decision analysis could have helped us, but our teams were not prepared to implement them in real time when this happened. And the last thing I want to just point out to you, there's which I really like. This is from Annie Duke, Thinking in Bets, her book. And if you watch the YouTube there, you'll see some, what I like about it is that it summarizes some really easy concepts like when you think about getting advice from people, don't think about just external people, but also think about yourself and think about your future self, your past self, and your present self. So she just gives a really nice conceptual way of thinking about this. Okay, I'm pretty much ending. I'm just going to end with this slide, which I'm reading the book, Decision Making Under Deep Uncertainty, and it is providing for me this overall framework. I really liked what Dr. Lempert presented at the very beginning. Let me go ahead and come out of the slide set here, because I think the book provides some really nice conceptual diagrams that helps organize in my mind, really moving from prediction to action to really think about robust plans. It's easier for me to get together with a team of people and say, okay, what goals are we trying to accomplish? What are our plans? Are our plans going to be robust across different scenarios? I can do that pretty quickly. And so I'm really excited about starting off with that kind of framework and then using the more rigorous analytic approaches if we have time and expertise. California is a great place. CDPH is a great place to work with. We're going to be hiring for a decision intelligence unit. We're going to have a multidisciplinary team of people to work on developing this process over time. So I'd be really excited to be able to work with other folks. Thank you.
Yeah, thank you, Tomás. So I think Rob is there, and if you're a speaker, you can come on camera. Even if you're not, you can also come on camera if you like. And yeah, Rob, do you have like any parting thoughts and a way to summarize all of this in 30 seconds? But we can stay a little bit longer if people have patience.
I actually do need to run pretty near the top of the hour. Yeah, no, I mean, first off, this was wonderful. Thank you so much for organizing this, Pedro. I mean, just a real wonderful mix of practical, how does it work in practice, and then the research. If we had more time, it'd be fun to talk with Tomás and Crystal about the the Eisenhower quote of plans are useless and planning is everything, and how that obviously initially taken from the military context, where you probably have more time to plan and then even less time to respond when the plan breaks. How that maps on to how you set that up. Though Tomás, I think you probably covered a lot of that in the stuff you laid out. I have to kind of think about that, but yeah, I mean, mostly just thanks at this point.
Thank you.
And what are next steps?
No, I'm really inspired by your work, and I think you've given us for me, it's a paradigm shift from going from prediction to action to focusing on robust planning, because I feel like they're like two sides of the same coin. And I think they really complement each other. And I think from a human team perspective and human psychology perspective, the robust planning is easier to implement. And you can bring people along as we learn how to integrate the more quantitative approaches.
Great.
Yeah. Well, I want to thank everyone. We are 1 minute above our hour. So thank you all for joining. Had a good showing. I did leave a link in the chat for a sign-up page where you just put your name, your email, and then you get updates from this group. The DMDU in Health Special Interest Group meets every quarter, so you can join those meetings and also suggest to present your work, and we'll move this discussion forward. And thanks to all the speakers and everyone who contributed to this. Thank you. Okay, thank you, and have a nice rest of your day.
Thank you. This was great.
Thanks. Bye-bye.
Bye.
Yeah.
Thank you.